Beyond every planet, beyond every spacecraft ever launched, the Sun still holds onto something enormous, a shell of icy debris so wide that a beam of light takes nearly 2 years to cross it, and so far away that the Sun itself would shrink to little more than a bright point of light in a dark sky, one star among billions. Astronomers call it the Oort cloud, and for decades they inferred its existence purely from where certain comets seem to come from, long before any instrument could see a single piece of it directly. This is the story of that invisible shell. How a Dutch astronomer's simple arithmetic in 1950 first revealed it, what it is actually made of and how it got there, why it defines the true edge of our solar system far beyond anything we normally picture, and what its slow billion-year unravelling reveals about how fragile even a star's gravitational grip really is. Through most of the 20th century, astronomers cataloguing comets kept running into the same puzzle. Most comets they knew well, the ones that swing past the Sun every few years or every few decades, travel on orbits confined to roughly the same flat plane the planets follow, the same disc-shaped track along which Earth, Jupiter and the rest circle the Sun. But a smaller, stranger group of comets refused to behave that way. These comets fell in from every direction imaginable, tilted at every angle to the plane of the planets. Some arriving nearly straight down from what would be directly overhead of the solar system, and others rising up from directly below it. When astronomers calculated how long it would take these comets to complete one full orbit, the numbers came back in the millions of years. A comet that takes a few decades to orbit the Sun has clearly been swinging past for a long time already, and its path is well understood. But a comet that takes 1,000,000 years to return will not be seen again by anyone now alive to remember its first appearance. Every long-period comet astronomers observed arriving for the first time in recorded history was, by definition, coming from somewhere far outside anything then mapped. Long before anyone framed the puzzle this precisely, comets had already been terrifying and fascinating human observers for thousands of years, recorded in the astronomical annals of ancient China, in Babylonian tablets, and in medieval European chronicles that often described a sudden bright comet as a portent of disaster, a plague, a fallen king, or an approaching war. What none of those ancient observers could have known is that many of the brightest and most memorable comets in the historical record, appearing once, blazing brilliantly for a season, and then vanishing for what amounted to the remainder of recorded human history, were long-period comets of exactly the kind that would eventually point Oort toward his reservoir. Single visits from objects that, statistically, are extremely unlikely to be seen twice by the same civilization, let alone the same person. The obvious question was where that somewhere might be. The comets themselves were small, faint objects, glowing only because sunlight warmed their icy surfaces, enough to shed a thin trail of gas and dust, visible for a few months as they neared the Sun, and then gone again, for what would be a return date longer than the whole of recorded humans' history. Tracing their incoming paths backward gave astronomers a rough direction and speed, but no comet arrived carrying a label attached to explain its origin. Several early ideas were floated and discarded. One suggestion held that these comets were captured interstellar wanderers, ice fragments drifting freely between stars that happened to pass close enough to the Sun to be pulled briefly onto a solar orbit before continuing on their way. That idea ran into a problem. If the comets truly came from interstellar space, their incoming speeds should show a signature of that origin, a slight excess of velocity left over from their travel between stars. When astronomers actually measured the speeds of newly discovered long-period comets, that excess was missing. Comet after comet arrived on an orbit that looked, in an important technical sense, like it was barely bound to the Sun at all, moving just slowly enough that the Sun's gravity could still, just barely, pull it back rather than let it escape forever. That is a very specific and very telling signature. It does not look like an object dropping in from far outside the solar system. It looks like an object that was already gravitationally attached to the Sun, sitting quietly at some enormous distance, until something nudged it loose and sent it falling inward for the first time. That distinction matters enormously, and it is the thread this whole episode follows. An object barely bound to the Sun, rather than one arriving from truly interstellar space, must have a home somewhere within the Sun's own gravitational reach, however far out that reach might extend. The orbits pointed to a reservoir, not a random population of interstellar drifters. But no telescope of the era, and in fact no telescope built since, has ever been powerful enough to see that reservoir directly. Its members are simply too small, too dark, and too far away, reflecting only the faintest trickle of sunlight back across a gap that dwarfs the distance to every planet combined. So the population had to be inferred, the way a detective infers the shape of an unseen object from the pattern of shadows it casts, using nothing but the trajectories of the handful of comets that occasionally, rarely, fell close enough to the sun to be caught and measured. By the middle of the century, this pattern of evidence, a scattering of comets on nearly unbound orbits, arriving from every direction rather than from one flattened plane, and showing no sign of a true interstellar origin, had accumulated enough weight that it demanded a real explanation, not just a guess. The scattering itself was the clue. If long-period comets arrived from every direction with roughly equal likelihood, then whatever was sending them must itself surround the sun in every direction, not sit off to one side or confined to a disk the way the planets do. That is an unusual shape for anything in the solar system. Every large structure astronomers already knew, the planets, the asteroid belt further in, all traced out flattened, disk-like paths, a natural consequence of how the solar system's spinning cloud of gas and dust had collapsed and flattened billions of years earlier as it formed. Whatever was sending these particular comets clearly had not flattened the same way, or if it had once been part of that same disk, something had since pulled it up and out into a shape wrapped around the sun in every direction at once, top, bottom, and every side. Explaining how that could happen, and putting an actual number on how far away such a structure would need to sit, would take one astronomer's fairly simple arithmetic, done with the kind of care that turns a hunch into a testable hypothesis, and that arithmetic is where the next chapter of this story begins. The astronomer who did that arithmetic was Jan Oort, working at Leiden Observatory in the Netherlands, already well known for earlier work mapping the shape of our own galaxy from the motion of gas clouds. In 1950, Oort turned his attention to the growing catalogue of long-period comets, and asked a very specific testable question. If these comets really were being nudged loose from some distant reservoir, how far away would that reservoir have to sit for the numbers to work out? He was not guessing. He took the small set of well-measured long-period comet orbits available to him, several dozen at most, and worked backward through their energies and their distances at the point where the sun's gravity had first started shaping their paths. The physics behind the calculation is not exotic, but it does require a plain English gloss, because the term at the centre of it, gravitational binding energy, sounds abstract until it is tied to something physical. Every object orbiting the sun carries a certain amount of energy tied up in its motion and its position. An object on a tight, fast orbit close to the sun, like Earth, has a large negative binding energy, meaning it is held very firmly, and would need an enormous push to ever escape. An object out at the very edge of where the sun's gravity can still meaningfully compete against the pull of everything else in the galaxy, has a binding energy close to zero, meaning it is barely held at all, one gentle nudge away from either falling inward for the first time or drifting off into interstellar space forever. When Oort measured the binding energies of his sample of long-period comets, he found them clustered right around that near-zero threshold, again and again for comet after comet. That clustering was the signal. It meant these comets were not falling in from a wide range of starting distances. They were falling in from roughly the same distance, a distance so far out that the sun's grip on them was only just barely stronger than the competing pull of the rest of the galaxy. Putting a number on that distance meant balancing two forces against each other: the sun's own gravity, which weakens the farther out you go, and the collective gravitational pull of everything else, the passing stars, the giant clouds of gas drifting through the galaxy, and the slow, steady pull of the galaxy's disk itself, tugging gently on anything orbiting too far from the sun to feel that stars grip strongly. Oort's arithmetic placed the balance point, and therefore the reservoir, at somewhere on the order of 20,000 to 200,000 astronomical units from the sun. An astronomical unit, the standard yardstick astronomers use for distances in the solar system, is the average distance from Earth to the sun, about 150 million kilometers. So even the lower end of Oort's estimate placed this reservoir at roughly 20,000 times farther from the sun than Earth is, and the upper end pushed that out by a further factor of 10. Nothing else known in the solar system at the time sat anywhere close to that far out. Neptune, the outermost planet then confirmed, orbits at only 30 astronomical units. Oort's reservoir, whatever it turned out to be, was proposed to sit somewhere between 600 and 6,000 times farther out than Neptune's own orbit. There was a second, equally important part of Oort's reasoning, addressing the shape question left open at the end of the previous chapter. Since long-period comets arrive from every direction across the sky, with no preference for the flattened plane the planets occupy, the reservoir sending them had to be roughly spherical, a shell surrounding the Sun in all directions rather than a disk confined to one plane. Oort proposed that this shell had likely formed from material originally much closer in, material left over from the same disk of gas and dust that built the planets, but which had been gravitationally flung outward early in the solar system's history, and, crucially, had its orbit's tilt scrambled along the way by repeated gravitational encounters until what began as a flattened population of debris ended up smeared into a sphere. This matched the evidence perfectly, a spherical shell of leftover material, sitting at a truly enormous distance, occasionally nudged by outside gravitational influences into orbits that would carry a member of it plunging back toward the Sun for the first time in the age of the solar system. Nobody has ever photographed a single member of this shell directly, not in 1950 and not now, more than 70 years later, and that fact alone tells you something about scale that no number by itself quite conveys. The shell's existence rests entirely on inference from the orbits of the handful of comets it has ever sent our way, the same kind of reasoning that let 19th century astronomers infer the existence of Neptune from wobbles in Uranus' orbit before anyone had ever seen it through a telescope. Oort's name stuck to the reservoir he had inferred, and the Oort cloud, as astronomers now call it, has since been refined, subdivided, and mapped in far greater statistical detail, using thousands of comet orbits rather than dozens. But the basic shape of the answer, a vast spherical shell of icy bodies at tens of thousands of astronomical units, has held up for more than 70 years of scrutiny. What that distance actually feels like, translated into terms a person can hold in their head, rather than just a number on a page, is where the story turns next. In the decades since Oort's original estimate, thousands more long-period comets have been tracked, their orbits measured with a precision his 1950 calculation could never have achieved, and that larger dataset has let astronomers do something Oort's handful of comets could not. Split the single reservoir he proposed into two distinct zones, each with no character and its own likely origin. The nearer of the two zones is now generally called the inner Oort cloud, or sometimes the Hills cloud, after the astronomer who first argued for its existence as a separate structure. It begins at roughly 2,000 astronomical units from the Sun, already 50 times farther out than Neptune's own orbit, and extends out to somewhere around 20,000 astronomical units. Within this inner zone, models suggest the shape is not a perfect sphere, but something closer to a thick, donut-like ring, retaining a partial memory of the flattened disk the material originally came from, because objects this glows in have not yet had their orbits fully scrambled by outside gravitational influences. The inner cloud is also thought to hold the vast majority of the total mass of icy bodies in this whole outer reservoir, simply because gravity concentrates material more efficiently at shorter distances. The same reason a marble rolled into a wide shallow bowl settles near the bottom rather than spreading evenly across the rim. Beyond roughly 20,000 astronomical units begins what astronomers call the outer, or classical, Oort cloud, and this is the true spherical shell that Oort originally inferred. Current estimates place its outer edge somewhere between 100,000 and 200,000 astronomical units from the Sun, though the exact boundary is genuinely uncertain, and astronomers hedge accordingly, because at that distance the Sun's own gravity has weakened to the point where it is only barely stronger than the competing pull of the rest of the galaxy, and small uncertainties in that competing pull translate into large uncertainties in exactly where the Sun's influence finally gives out. Within this outer shell, unlike the flattened inner donut, orbits point in every direction with no preference at all, a true sphere built from material whose tilts have been thoroughly scrambled over billions of years of gravitational encounters, exactly the shape the long-period comet orbits originally demanded. How many individual objects actually populate this two-part structure is one of the harder numbers in all of astronomy to pin down, precisely because so few members have ever been directly observed. Rather than account from direct observation, the estimate comes from working backward. Astronomers know roughly how many long-period comets arrive at the inner solar system per century. They have a reasonably good model for what fraction of the reservoir gets nudged loose and sent inward over that time, and they can run that math in reverse to estimate the total population required to sustain the observed arrival rate over the age of the solar system. That backward calculation currently points to something on the order of 1 trillion or more objects larger than about 1 kilometer across, scattered through the full Oort cloud, alongside untold billions more smaller fragments too small to ever survive the multi-million-year plunge to the inner solar system intact. 1 trillion is a number too large for most people to hold any real intuition for, so it is worth pausing on it directly. If every single object in the Oort cloud were a grain of sand, 1 trillion grains would fill roughly a large moving truck. Scattered instead across a spherical shell roughly 2 light-years across, that same trillion objects sit, on average, tens of millions of kilometers apart from their nearest neighbor, each one an isolated point of matter surrounded on every side by nothing at all. That last fact matters for a comparison worth making explicitly, because it corrects a common and understandable misconception. It is tempting to picture the Oort cloud the way an artist's illustration usually renders it, as a dense, glittering swarm of icicles crowded shoulder to shoulder around the solar system. The reality is closer to the opposite. The Oort cloud is, by any reasonable measure of density, one of the emptiest structures astronomers ever discuss, its trillion or so members separated by gaps so large that a spacecraft could cross the entire structure and have no meaningful chance of ever passing near a single one of them. Scale and density are not the same thing, and the Oort cloud is a case where a structure can be almost incomprehensibly vast while still containing almost nothing per unit of volume. Making that vastness actually felt, rather than simply stated as a number, is worth doing carefully, and that is exactly where this story turns next. To feel the true scale of the Oort cloud rather than simply hear it stated as a number, it helps to walk the same journey a real spacecraft is already making. Voyager 1, launched in 1977, is the fastest and farthest travelling object human hands have ever built, moving away from the Sun at roughly 17 kilometers every second, fast enough to cross the distance from New York to London in about 5 minutes. It has already left the heliosphere, the bubble of the Sun's outward streaming particles, and is now travelling through interstellar space in every meaningful sense of the term. And yet Voyager 1, moving at that tremendous speed, will not reach even the near edge of the inner Oort cloud for roughly another 300 years. It will take on the order of 30,000 years, 10 times longer than the entire span of recorded human civilization, to cross all the way through the Oort cloud and finally leave it behind for good. No human institution and arguably no single human language has ever remained continuous for even a tenth of that span. The spacecraft will simply still be crossing empty space, decade after decade, century after century, long after every trace of the civilization that built it has changed beyond recognition. Light itself, the fastest thing in the universe and the standard astronomers use to measure truly large distances, takes about 8 minutes to reach Earth from the Sun. It would take roughly a full year to cross the inner edge of the Oort cloud at 2,000 astronomical units, and something closer to 2 full years to cross the entire structure from its inner boundary to its outer edge, near 100,000 to 200,000 astronomical units. Put another way, the Oort cloud alone, this one loosely bound shell of leftover ice orbiting a single star, is wider than the distance light travels in a year, wide enough that it starts to compete on the same scale astronomers normally reserve for measuring the gaps between entire star systems, not the contents of a single one. A useful comparison for the outer boundary specifically, the nearest star system to our own, a triple system built around a small dimmed red star called Proxima Centauri, sits about 4.24 light-years away, or roughly 268,000 astronomical units. That means the outer edge of our own Sun's Oort cloud, by some estimates, reaches out to somewhere between roughly 1/3 and 3/4 of the entire distance to the next star system over. The Sun's gravity, in other words, does not politely stop at some tidy boundary well clear of the neighbours. Its zone of influence, sparse and weak as it becomes out there, may extend a substantial fraction of the way to the next star, and if Proxima Centauris' own surrounding shell of debris, assuming it has one of comparable size, extends a similar fraction of the way back toward us, the two shells may come close to touching, or even slightly overlapping, out in the space between the stars, two nearly empty spheres brushing against each other's outermost, most tenuous edges. It is worth being honest about how strange this makes the very question of where one star's solar system ends and the space between stars begins. Most popular illustrations of the solar system draw a hard edge somewhere just past Neptune or just past Pluto, a clean line implying that everything past it is simply interstellar space, no longer part of the Sun's domain. The Oort cloud makes clear that no such hard line exists in nature. Instead, there is a long, slow fade, a gravitational influence that weakens gradually over tens of thousands of astronomical units rather than switching off, so that the honest answer to where the solar system ends is not a distance at all, but a description. It ends wherever the Sun's weakening pull finally loses, definitively and permanently, to the combined pull of everything else in the galaxy, a boundary that is fuzzy, directionally uneven, and genuinely still being refined by researchers today. None of this vast outer shell formed where it now sits. Every one of the trillion or so icy bodies scattered through it began its existence far closer to the Sun, in the crowded, violent nursery where the planets themselves were being assembled, and understanding how something that started life close to home ended up flung out to a fifth of the way to the next star is the next thread this story has to pick up. Every icy body drifting through the Oort cloud today began its existence in a completely different part of the solar system, and tracing that journey backward is one of the more satisfying pieces of detective work in modern planetary science. The solar system formed roughly 4.6 billion years ago from a single rotating cloud of gas and dust that collapsed under its own gravity, flattening as it spun into a broad disk with the young Sun growing at its center. Within that disk, solid material closer to the Sun, where temperatures stayed too high for ice to survive, condensed mostly into rock and metal, eventually building the 4 inner rocky planets. Farther out past a boundary astronomers call the frost line, where temperatures dropped low enough for water, ammonia, and other common compounds to freeze solid, the raw material available to build new bodies included enormous quantities of ice as well as rock. This colder, icier zone of the disk is where the 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, assembled themselves, and it is also where most of the material that would eventually become the Oort cloud first took shape, as countless smaller icy bodies called planetesimals, ranging from mountain-sized chunks to small worlds hundreds of kilometers across. The giant planets did not form quietly and stay put, as Jupiter and Saturn in particular grew massive enough to dominate the gravity of everything nearby. They began scattering the smaller icy planetesimals around them with tremendous violence. A planetesimal passing close to a growing giant planet gets its orbit reshaped by that planet's gravity in a single encounter, sometimes gaining enough energy in that one pass to be flung outward onto a far larger, far more elongated orbit than it started on. Jupiter, being the most massive of the 4, was also the most efficient at this kind of scattering, and it is now understood to have ejected an enormous fraction of the icy material that once occupied its part of the disk, sending much of it outward past Saturn, past Uranus and Neptune, and eventually out beyond the reach of any planet's gravity entirely. Saturn, Uranus, and Neptune all did the same to varying degrees, each throwing some of the disk material they encountered outward, rather than incorporating it into themselves or their moons. It is worth distinguishing this process clearly from a separate, closer reservoir of icy bodies that also formed beyond the frost line. The Kuiper Belt, a disk-shaped region beginning just past Neptune's orbit and extending out to roughly 50 astronomical units, home to Pluto and a great many smaller icy worlds. Objects in the Kuiper Belt, unlike the material flung out to build the Oort cloud, mostly stayed on flattened, disk-like orbits similar to the planets, because they were never ejected outward violently enough, or far enough, for the galactic tide and passing stars to round their orbits into a sphere the way they did for the material that became the Oort cloud. The 2 reservoirs share a common birthplace and a similar icy composition, but only one of them, the far more distant and far more thoroughly scattered one, ended up wrapped around the Sun in every direction. This process explains something that would otherwise be a genuine puzzle. How material now sitting tens of thousands of astronomical units from the Sun came to be composed of ices and compounds that chemically look like they formed much closer in the specific temperature zone near the giant planets, rather than in some exotic environment far out in the cold dark where the Oort cloud now resides. The chemistry is a fingerprint. Comets that fall in from the Oort cloud and get analysed by telescopes as they warm near the Sun show ratios of water, carbon monoxide, carbon dioxide, and other compounds consistent with formation in that giant planet zone, not consistent with having condensed originally at the enormous distances where they are found today. The bodies did not form far away. They were built close to home and then thrown out, a process closer to a slingshot than a slow drift. Being flung outward on a wildly elongated orbit is not by itself enough to build a stable reservoir like the Oort cloud, though. An object flung outward by Jupiter typically ends up on an orbit that still swings back close to the Sun on its inward leg, meaning it still passes near Jupiter or one of the other giant planets, over and over again on each successive lap, risking another violent gravitational encounter each time, one that might just as easily eject it from the solar system altogether as push it farther out. For an object to end up gently parked in a large stable orbit far from the Sun, rather than eventually thrown out of the solar system entirely, something else had to intervene once it had already been flung out to a great distance, something operating on a much larger scale than any single planet, gently rounding off the outer part of its orbit so it would stop swinging back through the dangerous inner solar system altogether. That gentler, larger scale sculptor is the subject the next chapter turns to. An object flung outward from the region of the giant planets starts life on a long, narrow, elongated orbit, one that still dips back in close to the Sun and close to whichever giant planet gave it that first violent push on every single lap. Left alone, most such objects would eventually suffer a second close encounter with a giant planet, and either be thrown out of the solar system entirely, ejected as a rogue object drifting forever between the stars, or pulled back into a tighter orbit and eventually consumed. What actually happened to the survivors, the icy bodies that make up today's Oort cloud, required something to intervene from outside the solar system entirely, something with enough reach to act on an object even at the farthest point of its long, elongated orbit, far beyond where any planet's own gravity could still touch it. That outside influence has two parts, and both act slowly, over hundreds of millions of years rather than the single violent encounters that did the initial scattering. The first is called the galactic tide, the gentle but relentless gravitational pull exerted by the combined mass of the Milky Way's disk, all its stars, gas and dust taken together as it tugs on anything orbiting far from the Sun. Close to the Sun, this tug is utterly negligible compared to the Sun's own overwhelming gravity. But at the farthest point of a newly ejected object's elongated orbit, tens of thousands of astronomical units out, the Sun's own pull has weakened enough that the galaxy's tug, though still tiny in absolute terms, becomes large enough by comparison to matter. Acting over and over, orbit after orbit, across hundreds of millions of years, the galactic tide slowly lifts the innermost point of these elongated orbits away from the dangerous inner solar system, the same region where a giant planet's gravity might otherwise catch the object on another close pass. Bit by bit, an orbit that once dipped all the way back in, near Jupiter, gets stretched and rounded until its innermost point sits safely out past even Neptune's orbit, permanently out of reach of any planet's gravity ever again. The second influence is the simple, cumulative effect of passing stars. The Sun, like every star in the galaxy, is in motion relative to its neighbours, and over the roughly 4.6 billion years since the solar system formed, an enormous number of other stars have drifted past at various distances, each one exerting its own small gravitational tug on anything orbiting far out in the Sun's outer reaches. No single passing star does very much on its own. Most passes are distant enough that the nudge is barely measurable. But summed across billions of years and untold thousands of individual stellar passages, the cumulative effect is significant, further randomizing the tilts and shapes of these far-out orbits, smoothing what remained of any directional preference left over from the flattened disk the objects originally came from, and helping complete the transformation from a scattering of elongated, planet-crossing orbits into the roughly spherical shell of gently rounded orbits that Oort's arithmetic first inferred. The result of these two slow processes acting together, the galactic tide doing most of the rounding and passing stars doing most of the final randomizing, is a genuinely elegant piece of celestial mechanics, material thrown outward by violent, chaotic, close-range gravitational encounters near the giant planets ends up, hundreds of millions of years later, parked in gentle, stable, nearly circular orbits at almost unimaginable distances, protected from ever suffering another violent encounter, precisely because it is now so far from anything with enough gravity to disturb it. It is a rare case in nature where chaos at close range produces order at extreme distance, and it explains why the Oort cloud, unlike the flattened disk of the planets and the asteroid belt closer in, wound up as a sphere, The very forces that built it operate equally in every direction, unlike a planet's gravity, which only acts along the plane where the planet itself orbits. It is worth pausing to name how strange this makes the phrase solar system belonging to the Sun. In an important sense, the outer Oort cloud belongs just as much to the Milky Way galaxy as it does to the Sun. Its final shape was set not by anything the Sun itself did, but by the combined pull of 100 billion other stars and the galaxy's own gravity acting across a scale of hundreds of millions of years. The Sun's role reduced at that distance to little more than a weak anchor holding these objects loosely enough that the galaxy's own gravity could finish the job of shaping them. None of this explains what any individual object out there actually looks like, or what it is made of, and that is the more tangible physical question this story turns to next. Strip away everything about where an Oort cloud object sits and how it got there, and what remains is a surprisingly modest piece of matter, a comet nucleus, the solid core that becomes a comet only once it nears enough sunlight to start shedding gas. Direct measurements of nuclei come almost entirely from a small number of comets that spacecraft have actually visited up close, since no probe has ever travelled remotely far enough to photograph an object still sitting in the Oort cloud itself. But those nearby comets share a common origin story with their more distant relatives, and the physical picture they reveal is consistent enough that astronomers apply it with confidence to the wider population. A typical nucleus is small by planetary standards, usually somewhere between 1 and a few tens of kilometers across, small enough that its own gravity is far too weak to pull it into a sphere, which is why comet nuclei tend to look lumpy, elongated, and irregular rather than round, closer in shape to a potato or a peanut than to a planet or moon. The material making up that irregular shape is a mixture that earned the nucleus its long-standing popular nickname, though modern measurements have refined that picture considerably. The bulk of a nucleus is water ice, mixed with a variety of other frozen compounds that would be gases at room temperature on Earth, carbon monoxide, carbon dioxide, methane, and ammonia among them, all locked solid at the extraordinarily low temperatures found this far from any star. Threaded through that ice is a substantial fraction of dark, carbon-rich dust and rocky grains, similar in some ways to the material found in certain types of meteorites, left over unaltered from the original disk of gas and dust the solar system's assembled from. This dust is what gives most comet nuclei their strikingly dark surfaces, some of the darkest natural surfaces ever measured on any object in the solar system, reflecting back only a few % of the sunlight that reaches them, several times darker than fresh asphalt. Perhaps the most surprising physical property, confirmed directly when spacecraft finally measured it on comets close enough to visit, is how loosely packed a comet nucleus actually is. Rather than a solid block of ice, a typical nucleus is closer to a weakly bound pile of ice and dust chunks, riddled with gaps and voids, giving it an overall density often lower than that of water ice itself, in some cases barely denser than compacted snow. If you could somehow transport an average comet nucleus down to Earth and set it in a swimming pool, a meaningful fraction of it, unlike a compact iceberg, might very nearly float rather than sink, held together by little more than its own extremely weak gravity and a scattering of frozen bonds between grains, fragile enough that a moderately close pass by a planet's gravity, or even the stress of its own spin, can be enough to tear a nucleus apart entirely, something astronomers have directly observed happen to several comets caught in the act of breaking into pieces. To make the size of a nucleus tangible, a comet nucleus roughly 10 kilometers across, a fairly typical size for the population, is comparable in its longest dimension to a modest-sized city or a long international runway laid end-to-end, small enough that if the nucleus were parked in orbit around Earth rather than out among the stars, it would be difficult to even see with the naked eye from the ground. And yet a single icy body scarcely bigger than a city, drifting alone through the void, is representative of the roughly trillion or so bodies that together make up the entire Oort cloud, each one this small, each one separated from its nearest neighbour by tens of millions of kilometres of absolute emptiness. Out at its resting distance in the Oort cloud, a nucleus like this experiences sunlight 1,000 times fainter or more than what reaches Earth, dim enough that the sun itself would appear as little more than an unusually bright star, too faint to cast a meaningful shadow or warm the ice by any measurable amount, and cold enough, at temperatures hovering only a few tens of degrees above absolute zero, that the frozen gases locked in the nucleus remain essentially inert, changeless, for the entire multi-billion-year history of the solar system, waiting. Waiting, as it happens, for exactly the kind of gentle gravitational nudge that eventually sends a small fraction of these ancient, unchanged bodies falling inward for the first time, and what that nudge actually looks like, and where it typically comes from, is the next part of this story. An object resting in a stable orbit tens of thousands of astronomical units from the Sun could in principle remain there for the entire remaining life of the solar system, held loosely by gravity too weak to ever change much of its own accord. Left completely alone, nothing would happen to it. But the Oort cloud is not left alone. It sits exposed, far more than anything closer to the Sun, to the gravitational traffic of the wider galaxy. And it is that traffic, not anything happening within the solar system itself, that periodically dislodges a small number of its members and sends them falling inward for the first time in billions of years. 3 distinct kinds of outside influence do most of this work, and it is worth naming each because they act on different scales and with different effects. The first is the same galactic tide already introduced as one of the forces that rounded these orbits into a stable shell in the first place. That same steady background pull from the mass of the galaxy's disk does not stop acting once an orbit is rounded. It continues nudging every object in the outer cloud a little, all the time, and for objects sitting at exactly the right distance and orientation, that steady nudge is enough, given enough time, to tip an orbit his innermost point back down into a range where it will finally swing close to the Sun. This process contributes a slow, steady background trickle of new comets spread roughly evenly over time. The second influence is the passage of an individual star. The Sun's neighbourhood in the galaxy is not empty. Other stars drift past at various distances and speeds continuously, and while most such passages happen at distances of several light-years or more, far too distant to disturb anything closer to the Sun than the outer edge of its own Oort cloud. The outer Oort cloud is exactly the part of the solar system exposed enough to feel even a fairly distant stellar passage. A star passing within a light-year or two, which happens on average every few million years, can measurably perturb a meaningful fraction of the outer cloud's population, potentially dislodging a batch of comets all at once, rather than the slow, steady trickle the galactic tide produces on its own. Astronomers have identified specific past and future stellar encounters close enough to matter, and tracking them is itself now an active area of study, matching the timing of ancient comet showers, inferred from impact craters and other geological evidence on Earth and the Moon, against the calculated timing of specific stars' closest approaches in the deep past. The third influence is rarer, but potentially more dramatic. The solar system's slow orbit around the centre of the galaxy, a single full circuit of which takes roughly 225 million years, occasionally carries it through denser regions of the galactic disk, including giant molecular clouds, enormous accumulations of gas and dust far more massive than any single star, sometimes containing enough material to briefly rival the tidal pull of the entire rest of the galaxy combined when the solar system passes unusually close. Such passages are rare on a human timescale, but not rare on a geological one, and some researchers have proposed that passages through unusually dense regions of the galaxy correlate with clusters of impact events on Earth, evidence, if the correlation holds, that the solar system's orbit through the wider galaxy is itself a variable that shapes how often the Oort cloud sheds material toward the inner solar system, though this particular link remains actively debated, and is one of the more genuinely unsettled claims in this whole area of research. Whichever mechanism does the nudging, the result for any individual affected object is the same. An orbit that was gently rounded and stable for billions of years gets tipped just enough that its innermost point drops from somewhere safely beyond Neptune down into a range where it will, for the first time since the solar system's early chaos, swing back in past the giant planets and toward the Sun itself. From the moment of that nudge, the object is committed to a journey that, given the distances involved, will take on the order of 1 million years or more to complete, a journey through emptiness so profound that for almost the entire trip nothing observable happens at all, right up until the final stretch, when sunlight finally becomes strong enough to matter, and that final stretch, the actual fall, is where the story goes next. Once nudged loose, a comet nucleus begins a fall that dwarfs, in duration, almost anything else discussed in ordinary human experience. Starting from a distance of tens of thousands of astronomical units, and moving under nothing but the Sun's own steadily strengthening gravity as it draws closer, A typical newly released comet takes somewhere on the order of 1 to several million years to complete the inward leg of its journey to the region near the Sun, where it will finally become visible. For almost the entire duration of that fall, nothing observable happens to it at all. The nucleus simply drifts, silent, dark, and utterly unchanged. Sunlight too faint, even a few thousand astronomical units out to warm its surface by any meaningful amount, exactly as it has drifted unchanged for the billions of years it spent resting in the outer cloud before the nudge that set it moving. To hold that million-year fall in human terms, agriculture, writing, and every human city that has ever existed all fit comfortably within roughly the last 10,000 years, 1% or less of the time a single comet spends completing this one inward fall. A comet nudged loose from the Oort cloud around the time the first stone tools were being shaped by early humans would, on the low end of typical fall times, still be less than 1% of the way through its journey today. The comets astronomers actually observe arriving right now were set in motion, in most cases, long before any human being existed, to eventually build the telescopes that would one day watch them arrive. It is worth contrasting this million-year fall with the far more familiar case of Halley's Comet, whose roughly 76-year orbit makes it entirely unlike the long-period comets this story has followed so far. Halley's Comet, though genuinely ancient, no longer belongs to the Oort cloud reservoir at all. Repeated close passes by the giant planets over its long observational history, stretching back to at least 240 BCE in the Chinese astronomical record, have progressively shrunk and reshaped its orbit into the short, tight loop seen today, a reminder that some fraction of Oort cloud comets, rather than being ejected or destroyed on their first return, get gravitationally captured into much shorter, far more frequently observed orbits instead, effectively graduating out of the Oort cloud population altogether. Nothing changes for the comet, physically, until it crosses a threshold, usually somewhere in the outer reaches of the region occupied by the giant planets, several astronomical units from the Sun, where sunlight finally becomes strong enough to begin warming its surface past the point where the most volatile frozen gases, substances like carbon monoxide, start to convert directly from solid ice into gas, without ever passing through a liquid phase, a process called sublimation. This first faint activity is often what allows astronomers to detect an incoming long-period comet, years before it reaches the inner solar system, spotting a faint fuzzy glow called a coma around what would otherwise be an essentially invisible point of reflected sunlight, the first visible sign that this particular nucleus, after a million-year silent fall, is finally close enough to the Sun to begin reacting to it. As the comet continues inward past the orbit of Jupiter and then Mars, the warming intensifies and the activity grows correspondingly more dramatic. Water ice, far more abundant in the nucleus than the more volatile gases that activated first, begins sublimating in earnest, releasing enormous quantities of gas and, critically, carrying loose dust grains along with it as that gas escapes from the nucleus' weak gravity into space. This escaping mixture of gas and dust forms the visible coma, an atmosphere of sorts, often growing to span tens of thousands of kilometers, dwarfing the tiny solid nucleus at its center, which by this stage may be only a few kilometers across, buried invisibly deep inside, a cloud of its own making that a small telescope on Earth can sometimes make out clearly. The comet's true signature, the long glowing tail that has made comets objects of fascination and, historically, of fear and superstition across nearly every human culture that ever recorded one, forms only in the comet's final approach to the Sun, shaped and pushed by two separate physical forces rather than one. Sunlight itself exerts a real, measurable pressure on the fine dust released from the nucleus, gently pushing it into a broad, curved tail that trails behind and slightly outward from the comet's path. Separately, the solar wind, the continuous outward stream of charged particles the Sun emits in every direction, interacts with any electrically charged gas in the coma to sweep it into a second straighter tail that points almost directly away from the Sun, regardless of which direction the comet itself happens to be travelling. Both tails, remarkably, always point roughly away from the Sun, rather than trailing behind the comet's direction of motion, which is why a comet's tail can sometimes appear to lead the comet as it moves away from the Sun on its outbound leg, sweeping ahead of it rather than behind, an effect that puzzled observers for centuries before the physics of sunlight pressure and the solar wind was properly understood. What happens to the comet once it actually reaches its closest approach to the Sun, and whether it survives that encounter to make the long return journey back out toward the Oort cloud, is not guaranteed, and that uncertainty is where the next chapter picks up. Reaching the Sun is not the end of a comet's story, and what happens next depends heavily on exactly how close it passes and how much of its icy material has already been driven off by the time it arrives. Most long-period comets from the Oort cloud pass no closer to the Sun than roughly the distance of Mercury or Venus, close enough to trigger dramatic sublimation and produce a spectacular coma and tail, but not so close that the encounter itself threatens to destroy the nucleus outright. A comet on this kind of orbit sheds a meaningful fraction of its ice and dust on each close pass, loses considerable mass overall, and then continues on, following the outbound half of its long elongated orbit back out toward the Oort cloud, headed for a return trip that, depending on how strongly its orbit was reshaped by the encounter, and by any close passes near the giant planets on the way in or out, might not happen again for hundreds or even thousands of years. Comet Hale-Bopp, discovered in 1995, and visible to the naked eye for a record-breaking stretch of roughly 18 months across 1996 and 1997, is one of the best documented examples of exactly this kind of comet. Its nucleus, estimated at somewhere between 40 and 80 kilometers across, unusually large for a long-period comet, is thought to be why it produced such a bright, long-lasting display even though its closest approach to the Sun never brought it closer than roughly the orbit of Mars, farther out than many far less spectacular comets pass. Having survived its passage, Hale-Bopp is now well on its way back out on the long outbound leg of its orbit, and current calculations suggest it will not return to be visible from Earth again for roughly another 2,500 years, a date far enough in the future that no currently living person, and likely no civilization that presently exists, will be present to observe it. Not every comet survives its encounter with the Sun so cleanly. A smaller fraction of long-period comets, called Sungrazers, follow orbits that carry them extremely close to the Sun's surface itself, sometimes within a few solar radii, close enough that the intense heat and the Sun's powerful tidal gravity, the difference in gravitational pull between the side of the nucleus facing the Sun and the side facing away, can be enough to tear a fragile, loosely bound nucleus apart entirely during the encounter. Space-based solar observatories, originally built to study the Sun itself rather than comets, have inadvertently become the most prolific comet discovery instruments in history, precisely because they continuously watch the region right around the Sun where sun-grazing comets make their final, often fatal approach, and have recorded thousands of such comets breaking apart and vaporizing entirely within view of their cameras, visible for only hours or days before disappearing forever, their material scattered as gas and dust that eventually disperses into the broader solar wind. A comet's fate at the Sun, then, sits somewhere on a spectrum between two extremes. An orbit that passes comfortably outside any dangerous zone, sheds a survivable fraction of its ice on each pass, and returns on a long stable cycle potentially for millions of years, and an orbit that carries it so close that the very first encounter with the Sun is also its last. The nucleus destroyed in a single violent, brief event after surviving essentially unchanged in deep freeze for the entire multi-billion-year age of the solar system up to that point. Either way, a comet's mass only ever decreases with each solar encounter, meaning even the survivors are, slowly, being worn away, and a long-period comet that makes repeated close approaches over many thousands of years will eventually either be reduced to a small, inert, ice-depleted remnant, or lose so much structural cohesion from repeated thermal stress that it simply crumbles apart on some future pass regardless of how far from the Sun that particular pass happens to occur. This is one of the quieter, less dramatic threads of the whole Oort cloud story, but it matters for understanding the reservoir as a whole. Every comet the Oort cloud ever sends inward represents a genuine, permanent loss from the total population, material that either burns off entirely or gets reduced past the point of ever producing a visible comet again, meaning the Oort cloud, vast as it still is, has been slowly, steadily draining since the earliest days of the solar system, a fact that becomes important much later in this story, when the discussion turns to the cloud's own long-term future rather than the fate of any single comet passing through it. For now, though, the story returns to a more immediate, tangible question. What would it actually take, using the tools human civilization has actually built, to visit this reservoir directly, rather than simply wait for pieces of it to occasionally fall our way? Exactly 5 spacecraft launched by human beings are currently on trajectories fast enough to eventually leave the solar system for good. Pioneer 10 and Pioneer 11 launched in the early 1970s, Voyager 1 and Voyager 2 launched in 1977, and New Horizons launched in 2006 and famous for its close flyby of Pluto in 2015. Each of these 5 is moving outward faster than the Sun's gravity can ever pull it back, meaning each one, left undisturbed, will continue drifting away from the solar system forever, never falling back inward the way a bound object eventually would. In that narrow technical sense, all 5 are already, or will eventually become, genuinely interstellar objects, no longer meaningfully part of the solar system at all. But leaving the solar system in that gravitational sense, and actually reaching the Oort cloud are 2 very different milestones, separated by an amount of time that exposes just how differently spacecraft engineers and astronomers measuring cosmic distances have to think about scale. Voyager 1, the fastest of the 5, moving away from the Sun at roughly 17 kilometers per second, is projected to take around 300 years to reach the near edge of the Oort cloud, and something on the order of 30,000 years to pass all the way through it. Voyager 2, travelling in a different direction and slightly slower, and the 2 far slower Pioneer probes will take even longer. New Horizons, the newest of the 5, is moving at a comparable speed to the Voyagers but started its journey much later, and from a different point in the solar system's orbit around the galaxy, and by most calculations will also need multiple centuries just to reach the Oort cloud's inner edge. None of that matters in a practical sense, because every one of these 5 spacecraft will fall silent long before any of those centuries pass. Each is powered by a radioisotope thermoelectric generator, a device that produces electricity from the steady radioactive decay of a small amount of plutonium, and that decay, while extremely long-lived compared to a human lifetime, is not infinite. The generators lose a small, steady percentage of their power output every year, regardless of anything the spacecraft does. Voyager 1 and Voyager 2, the longest-lived of the 5 by a wide margin thanks to careful power management by mission engineers who have spent decades progressively shutting down instruments to conserve dwindling electricity, are expected to lose the ability to power even their radio transmitters and finally fall silent sometime in the 2030s, roughly 6 decades after launch. The 2 Pioneer probes have already fallen silent, their last transmissions received in the early 2000s and 1995 respectively, meaning they are, right now, silently drifting outward, no longer able to send back so much as a single bit of data, and will continue drifting, unresponsive and unreachable forever. The gap between a spacecraft's operational lifetime, measured in decades, and the time required to physically traverse the Oort cloud, measured in tens of thousands of years, is not a close call or an engineering problem that better technology might someday close within a human lifetime. It is a gap of roughly 3 orders of magnitude, the same kind of gap as the difference between the time it takes to read a single sentence and the time it takes to live an entire human life. No spacecraft humanity has built or currently has any serious plan to build will ever transmit a single signal from within the Oort cloud, let alone from beyond it. Every one of the 5 current interstellar spacecraft will spend the overwhelming majority of their journey through the Oort cloud, and every century of that journey as inert, silent metal tumbling through absolute blackness, sending nothing back to the civilization that launched them, which will, by the time any of them reaches even the cloud's inner edge, have either transformed beyond recognition or ceased to exist in any form that would recognize the mission as its own. This is not a reason for despair so much as a genuinely useful corrective to a common misconception, one that deserves stating plainly. Leaving the solar system in the sense the news headlines used when Voyager 1 crossed the heliosphere in 2012 is not the same as leaving the Sun's gravitational domain, and it is certainly not the same as reaching, let alone crossing, the Oort cloud. There is a meaningful difference between the boundary where the Sun's outward-blown particles finally give way to the particles drifting between stars, and the far larger boundary, discussed only in the vaguest terms so far in this story, where the Sun's gravity itself finally loses to the pull of the rest of the galaxy. Untangling those 2 very different boundaries, and being precise about which one deserves the label the edge of the solar system, is exactly where the story turns next. When Voyager 1 crossed a boundary called the heliopause in August 2012, news coverage around the world reported, understandably but not quite accurately, that the spacecraft had left the solar system. What it had actually crossed was the outer edge of the heliosphere, an enormous bubble carved into interstellar space by the solar wind, the continuous outward stream of charged particles the sun sheds in every direction. Within the heliosphere, the solar wind dominates, pushing back against the thin gas and dust that fills the space between stars. At the heliopause, roughly 121 astronomical units from the Sun when Voyager 1 crossed it, the pressure of the solar wind finally drops to match the pressure of that surrounding interstellar material. And beyond that boundary, the particles filling space are no longer predominantly the Sun's own, but material drifting in from elsewhere in the galaxy. That is a real and meaningful boundary, and crossing it is a genuine milestone. The first time any human-made object has measured the properties of true interstellar plasma directly rather than inferring them from a distance. But it is a boundary defined by the behavior of a particle-scale wind, not by gravity. And gravity is a completely different kind of boundary, extending vastly farther. The Sun's gravitational influence does not stop at 121 astronomical units, or anywhere close to it. It continues weakening gradually, exactly as described earlier in this story, all the way out to the tens of thousands, and eventually the 100,000 or more astronomical units where the Oort cloud's outer edge is thought to lie. Comparing the two numbers directly makes the gap unmistakable. The heliopause sits at roughly 121 astronomical units. Even a conservative estimate of the Oort cloud's outer edge at 100,000 astronomical units is more than 800 times farther out than the heliopause. Voyager 1, having crossed the widely reported boundary in 2012, had at that point covered less than 1,000th of 1% of the distance it would need to travel to reach even the near edge of the true gravitational domain the Sun still holds. So which boundary deserves to be called the true edge of the solar system depends entirely on what question is being asked, and being precise about that question is worth doing carefully, because different serious scientific communities genuinely use different definitions for legitimate reasons. A heliophysicist, studying the behavior of the solar wind and how it interacts with the wider galaxy, reasonably treats the heliopause as the edge of the Sun's domain, because that is the boundary relevant to the physics they study. A dynamicist, studying orbits and gravity, reasonably treats the outer edge of the Oort cloud, or more precisely the point where the Sun's gravity is finally overtaken by the combined pull of the rest of the galaxy, as the true edge, because that is the boundary relevant to what stays bound to the Sun and what does not. Both are correct answers to different, equally legitimate questions, and most of the everyday confusion around what leaving the solar system actually means traces back to popular reporting, collapsing these two very different boundaries into one. A related concept astronomers sometimes invoke here is the Hill sphere, a standard technical term for the region around any object, whether a moon around a planet or the Sun in the wider galaxy, within which its own gravity dominates over the pull of some larger, more distant body. Applied to the Sun and the mass of the Milky Way, calculations for the Sun's Hill sphere relative to the rest of the galaxy produce values broadly consistent with the outer Oort cloud's own estimated extent, a satisfying cross-check between two very different ways of asking the same underlying question: how far can the Sun's gravity credibly claim to win? There is a third candidate worth naming too, distinct from both the heliopause and the Oort cloud, the outer edge of the region where the giant planets and the disk of icy bodies known as the Kuiper belt, which lies just beyond Neptune orbit. This planetary zone, sometimes casually described as the edge of the solar system in older textbooks, and in most illustrations that show planets orbiting neatly and then simply stop, ends at only around 50 astronomical units, closer to the Sun even than the heliopause, let alone the Oort cloud. If a person only ever learned the solar system from a schoolbook illustration showing 8 or 9 planets circling the Sun with nothing drawn beyond them, they would be missing not one but two entire additional structures, the heliosphere and the Oort cloud, both of which extend the Sun's meaningful influence dramatically farther, in the Oort cloud's case by a factor of more than 1,000 beyond even the region where Neptune orbits. The honest, complete answer then is that the solar system does not have a single edge at all, but at least 3, nested one inside another at wildly different scales. The region of the planets and the Kuiper belt at roughly 50 astronomical units, the heliopause at roughly 100 to 120 astronomical units, and the outer boundary of the Oort cloud, and with it the true limit of the Sun's gravitational dominance over interstellar space, at somewhere between 100,000 and 200,000 astronomical units. Only the last of these three genuinely marks where the Sun stops winning against the rest of the galaxy, and it is the Oort cloud, not the planets and not the solar wind, that actually defines that final gravitational frontier. Whether that frontier is ever crossed by something coming the other way, a star passing close enough to disturb our own Oort cloud directly, is a question this story has so far only gestured toward, and it deserves a fuller answer next. Because the outer Oort cloud extends so far from the Sun, reaching perhaps a fifth to three-quarters of the way to the nearest other star system, it is inevitable, given enough time, that other stars occasionally drift close enough to pass directly through it, rather than merely tugging on it from a distance, the way most stellar passages do. Astronomers have identified a small number of specific stars, using precise measurements of their current positions and velocities, run backward or forward through time, that are calculated to have passed, or will eventually pass, close enough to qualify as genuine intrusions into the Sun's own outer reservoir of icy bodies. The best-known case looking backward in time involves a dim red dwarf star, catalogued as Scholz's star after the astronomer who identified it, currently sitting about 20 light-years away and moving in a direction that, when its motion is calculated backward, suggests it passed within roughly 1 light-year of the Sun somewhere around 70,000 years ago, a distance that would have carried it directly through the outer portion of the Oort cloud. A star passing that close, even one as dim and low mass as Scholz's star appears to be, would exert a real, if modest, gravitational tug on any Oort cloud objects near its path, potentially nudging some small fraction of them loose and sending them, eventually, on the long inward fall described earlier in this story. Some researchers have proposed that this specific encounter may be reflected in a subtle uptick in long-period comet arrivals that current statistical models suggest should have occurred somewhere around that time frame, though this particular link between one named star's calculated path and any specific historical comet activity remains difficult to confirm directly and is treated by most astronomers as an intriguing but unproven hypothesis rather than an established fact. Looking forward rather than backward, the most significant predicted future encounter involves a star called Gliese 710, currently located a little over 60 light-years away in the constellation Serpens, but moving on a trajectory that current measurements, refined considerably by a European space mission that mapped the precise positions and motions of more than 1 billion stars across the galaxy, suggest will bring it to within roughly 1 light-year of the Sun, and possibly considerably closer in approximately 1.3 million years. Some of the more recent, more precise calculations put the likely closest approach at well under 1 light-year, close enough that Gliese 710 would pass directly through and meaningfully disturb a substantial portion of the outer Oort cloud, plausibly triggering a genuine spike in the rate at which comets get dislodged and sent falling toward the inner solar system over the following few million years, an event some researchers have described, with appropriate caution about the uncertainties involved, as a potential comet shower measurably elevated above the ordinary background rate. It is worth being honest about what this kind of prediction can and cannot tell us. Astronomers can measure a star's current position and velocity with real precision and project its future path with reasonable confidence over a timescale of 1 million or so years, but a star's velocity is itself subject to small ongoing perturbations from other stars and from the galaxy's own gravity that current instruments cannot fully account for that far in advance. So any specific number, whether it is Gliese 710's closest approach distance or the exact date of Scholz's star's past encounter, carries a real margin of uncertainty that grows the farther the prediction reaches into the past or future. What is not in doubt is the basic phenomenon itself. Passing stars close enough to disturb the Oort cloud directly are not a hypothetical possibility reserved for exotic scenarios, but a routine recurring feature of the solar system's multi-billion-year history, one that has almost certainly happened many times already, and will almost certainly happen many times again. None of these encounters, even the closest calculated ones, come remotely close enough to threaten the inner solar system directly, or to meaningfully disturb Earth's orbit, or to send anything resembling the dense, dramatic swarm of incoming comets that popular fiction sometimes imagines following a close stellar encounter. The realistic effect, even for a close pass like Gliese 710's predicted approach, is a modest, temporary elevation in an already low, steady background rate of comet arrivals, spread out gradually over a period of a few million years rather than concentrated into any single dramatic event. But these encounters are also a reminder that the Oort cloud is not a sealed, static structure, isolated forever from the rest of the galaxy. It is a genuinely open system, continuously exposed to outside gravitational influence over cosmic timescales, and that continuous exposure carries a longer-term implication for the cloud's own future that the story now turns to directly. Every process described so far in this story points toward the same long-term conclusion. The Oort cloud is not a permanent fixture of the solar system, sealed away forever at a safe distance, but a slowly, steadily draining reservoir, losing material continuously in more than one direction at once, and current models suggest it has already lost a substantial fraction of whatever it originally contained. Some of that loss happens the way this story is already traced. Comets nudged loose and sent falling sunward, eventually consumed or reduced to inert remnants by repeated close encounters with the Sun. But that particular pathway, dramatic as it is when it produces a bright visible comet, accounts for only a modest fraction of the cloud's total losses. Far more material, by most current estimates, is lost the opposite way, nudged not inward toward the Sun but outward, ejected entirely from the solar system by the same galactic tide and passing star perturbations that originally rounded these orbits into a stable shell in the first place. The same gentle, cumulative gravitational nudging that can, in one instance, tip an orbit's innermost point down toward the Sun can, in another instance, instead push an orbit's outermost point up past the threshold, where the Sun's gravity can hold it at all, sending the object drifting away permanently into true interstellar space, no longer bound to any star. One more anonymous rogue object added to what is now understood to be an enormous galactic population of similar unbound icy and rocky bodies wandering between the stars, far outnumbering by some estimates the bound planets and comets belonging to any single star system. Some of these free-floating icy objects have, in a handful of cases, actually been detected directly, not around the Sun but drifting alone through interstellar space, identified by brief gravitational lensing events, or more recently, by direct imaging surveys sensitive enough to spot faint, unbound objects passing near enough to be resolved. Extrapolating from the handful found so far to the full population implied by theory suggests that free-floating objects of roughly this size, ejected long ago from stars across the galaxy, may collectively outnumber the bound planets and comets belonging to any single star system, the Oort cloud's own losses being simply this galaxy's own ordinary background contribution to that vast anonymous population. Current models, built by running the combined effects of the galactic tide and typical stellar passages forward and backward across the age of the solar system, suggest that the Oort cloud we observe today, despite still containing on the order of 1 trillion or more objects, may represent as little as half, or by some estimates even less, of its original population shortly after it first formed. The other half or more, by this accounting, has already been lost, the large majority ejected outward into interstellar space over the roughly 4.6 billion years since the solar system's early chaos first flung this material outward from the region of the giant planets. This is a genuinely sobering number in the specific sense that word deserves here, not because it threatens anything, but because it means the Oort cloud is best understood not as a stable structure, holding steady but as a slow leak that has already been running for the entire history of the solar system, and shows no sign of stopping. That leak is expected to continue at a broadly similar pace for billions of years into the future, barring anything more dramatic. But something more dramatic is, in fact, coming on a timescale astronomers can already describe with reasonable confidence. In roughly 5 billion years, having exhausted the hydrogen fuel in its core, the Sun will begin the phase of its life astronomers call the red giant phase, expanding dramatically and becoming vastly more luminous than it is today. This transformation is expected to have a real, if modest, effect on the Oort cloud, because the Sun's total mass, and therefore the strength of its overall gravity, will decrease somewhat as it sheds material into space during this later stage of its life. Most models suggest by something on the order of 1/3 to 1/2 of its current mass over its remaining lifetime. A star with weaker gravity holds its most distantly orbiting material more loosely, and this loosening is expected to accelerate the rate at which the outer Oort cloud, already loosely bound, sheds objects into interstellar space, potentially stripping away a considerable further fraction of what remains during the Sun's final billion or so years as an ordinary star. Even without that dramatic final chapter in the Sun's life, the trajectory is already clear from the ordinary gradual processes acting today. Run the current rate of loss forward across the deep future, and the honest expectation is that the Oort cloud, as a coherent gravitationally bound structure surrounding the Sun, will not last forever. It will continue thinning, slowly for billions of years, most of its remaining material eventually stripped away into the general galactic population of unbound wandering ice and rock, long before the Sun itself reaches the true end of its own life as a star. The shell that took hundreds of millions of years to build after the solar system's early chaos, and that has been leaking steadily ever since almost as long as it has existed, is, on the very longest timescales this story has discussed, a temporary structure rather than a permanent one, destined eventually to disperse back into the same wider galactic population of drifting material it was originally carved out of. What all of this, the puzzle that started this story, the arithmetic that solved it, the vast emptiness at its heart, and now its own slow unravelling, actually adds up to, in terms of how anyone should think about the true boundaries and true fragility of a solar system, including our own, is where this story now, finally, arrives. Return for a moment to the puzzle that opened this story, a scattering of comets arriving from every direction in the sky, on orbits so weakly bound to the Sun that they seem to belong to some reservoir sitting right at the ragged edge of the Sun's own gravitational reach. Jan Oort's arithmetic in 1950 turned that puzzle into a testable hypothesis, and 70 years of subsequent observation, spacecraft flybys of nearby comets, precise mapping of stellar motions across the galaxy, and statistical modelling of comet arrival rates has turned that hypothesis into one of the best supported, if still never directly observed, structures in the entire solar system. What that structure ultimately reveals is not really a story about comets at all, however striking any individual comet's million-year fall toward the Sun might be. It is a story about scale, and specifically about how badly the ordinary human intuition for a solar system, built almost entirely from schoolbook diagrams of 8 or 9 planets circling neatly around a central star, undersells what actually belongs to a star. The planets, spectacular as they are, occupy only the innermost sliver of the Sun's true domain, a region that ends at around 50 astronomical units. The Oort cloud extends that domain by a factor of more than 1,000 beyond that, out to distances that begin to seriously compete with the gap between entire star systems, reaching, by some estimates, between roughly 1/5 and 3/4 of the way to the Sun's nearest stellar neighbour. A star's gravity does not fade quietly at some polite distance well clear of the neighbours. It fades slowly, unevenly, and much farther than intuition expects, and only genuinely gives out where the combined pull of 100 billion other stars and the galaxy's own gravity finally overwhelms it. That fading, slow rather than sharp, is itself worth sitting with, because it changes the honest answer to a question that sounds simple but is not. Where does the solar system end? There is no single correct number. There is the edge of the planets and the Kuiper belt. There is the heliopause, where the solar wind gives way to interstellar plasma. And there is the true gravitational frontier at the Oort cloud's outer edge. 3 genuinely different boundaries nested one inside another, each correct for a different question, and only the last of the 3 marking the point where the Sun actually stops winning against the rest of the galaxy. Any illustration, any mental picture that draws a hard line just past Neptune and calls everything beyond it. Interstellar space is not wrong about the heliopause. It is simply answering a much smaller question than the one the Oort cloud forces onto the table. There is a second, quieter lesson buried in this story, one that only becomes visible once the cloud's own long-term fate is considered rather than just its shape and size. The Oort cloud is not a stable inheritance, sealed away forever once it formed. It has been leaking continuously for the entire 4.6 billion year age of the solar system, material nudged loose in both directions, inward toward a final fiery encounter with the Sun, and outward into the general drifting population of unbound material between the stars, so steadily that current models suggest as much as half of the cloud's original population may already be gone. Even a star as stable and unremarkable, by cosmic standards, as the Sun cannot hold on to its most distant possessions forever. Gravity at that extreme distance is a genuinely weak, precarious grip, constantly contested by the rest of the galaxy, and what looks from close up like a permanent structure surrounding the solar system is, on the timescale the rest of this story has used throughout, a slow, one-way process of dispersal that began the moment the cloud formed, and will not stop until long after the sun itself has changed beyond recognition. None of this diminishes the wonder of the thing. If anything, it deepens it. A single icy body, the size of a city, formed originally in the crowded, violent neighbourhood of the giant planets, gets flung outward by a chance gravitational encounter, spends hundreds of millions of years having its orbit slowly rounded by forces as large as the entire galaxy, rests then for billions of years in near-total darkness and near-total cold, farther from the sun than any planet, closer in a real sense to interstellar space than to home, until one day nudged by a star that itself formed around some other point in the galaxy entirely, and happened to drift close enough to matter, it begins, for the first time since the earliest days of the solar system, to fall. It falls for 1,000,000 years through absolute silence and absolute dark, and only in the final, briefest sliver of that 1,000,000-year journey, a sliver shorter than the span of recorded human history, does it finally do the one thing that lets anyone on Earth ever know it exists at all: catch enough sunlight to glow. That is the true scale of the Oort cloud, not simply a number of astronomical units, though the numbers are staggering enough on their own, but the improbable, almost accidental chain of events required for any single trace of this vast, dark, ancient, slowly dissolving structure to ever become visible to the small, warm, brightly lit world orbiting so very close to the centre of it all. The Oort cloud began this story as a puzzle, comets falling toward the sun from every direction, on orbits that hinted at something unseen, something vast waiting far beyond anything then mapped. It ends this story as a lesson in humility about scale itself. The sun's true domain, once the Oort cloud is counted, reaches roughly a fifth of the way, and by some estimates considerably farther, to the very next star, a domain built not by the sun alone but shaped over hundreds of millions of years by the combined gravity of the entire galaxy pressing in from every direction. Within that domain drifts a population on the order of 1,000,000,000,000 icy bodies, each one smaller than a modest city, separated from its nearest neighbour by tens of millions of kilometres of near-perfect emptiness, ancient beyond ordinary comprehension, and all of it slowly, steadily leaking away into the space between the stars. Every comet that has ever streaked across a night sky and startled or delighted the people watching it, from the earliest recorded civilizations to the astronomers tracking Hale-Bopp with modern telescopes, is a single grain from that vast, invisible, patiently dissolving shell, arriving after a fall of 1,000,000 years to remind a small, close, brightly lit world just how far its own star's quiet grip actually reaches.